Okay, so it was kind of funny giving a talk to the physics department about quantum anything. It's less funny to give it here. But hopefully it would be like, I mean, obviously it's a topic that's a mix of computer science and kind of quantum physics, quantum mechanics. We want to give the CS perspective and what we can learn from the CS perspective. So I started, I'm going to skip those, but I think they're still kind of important for this audience because it will kind of help us focus on what part of CS, at least in my experience and like my perspective on the work, was most kind of important and most helpful. So this is not really new, but I mean, we care about notation. And, okay, so we care about notation. And so languages and as a way of thinking and lambda calculi and so on. So defining a small language to define quantum is a worthy goal in some sense. So let me spend some time, because this is, for them, they kind of zoom through this very quickly. But here I want to spend a couple of minutes because I think it's an important idea. So when I started in, forgot when, like I was curious about quantum, one of the first kind of things that you encounter, quantum mechanics has to have the complex numbers. And there's a lot of discussion. Search for why complex numbers in quantum, and you find long explanations and long kind of philosophical slash mathematical slash physical kind of interpretation of why complex numbers are important and quantum mechanics must be complex. And fun papers, published research papers, quantum mechanics has to be complex, explaining why complex numbers are crucial. And then people try to build theories like quantum mechanics based on real numbers, based on p-adics, based on this, based on that. Nothing quite works. So it's like sometimes a big mystery. But from my perspective, for like this particular kind of point of view I have today, it's irrelevant. Why is it irrelevant? Because we can encode them. And if we talk about computational kind of properties and kind of what is the speed of computation or what a complexity class is or like a lambda calculus kind of picture, we don't care. Anything you can encode efficiently is fine. And so this is the encoding that you would get if you were trying to do quantum computing. So quantum computing has, for example, so this is a basic gate. It's like one of the phase gates, one of the simple phase gates. So the phase gates have here e to the I, some angle, and you can have as many angles as you want. And of course, if you have e to the I pi or e to the I, that's easy, but e to the pi theta for arbitrary theta, you get all kinds of complex numbers. So here is like a complex number, so you can encode it using this encoding. A vector of two complex numbers is coded as a bigger vector that has the real numbers but with a funny sign, because you need a funny multiplication. And then a matrix, you basically make it a block matrix. Every entry becomes a 2 by 2. And you can see this encoding, you can check all the properties, you know, its composition of this and that, addition, multiplication, everything works out. And so like instead of writing, for example, computation like this in a textbook of quantum computing, you would encode it this way and then never think about it again. So we don't care about complex numbers. So that's like a fundamental kind of shift in perspective in some sense between what the physicist would care about and what we kind of like our perspective. Of course, partial derivation, you know, people, question about execution, we know that. Even the physicists, you know, they use Mathematica a lot, so they're happy with that. But I think it becomes relevant because there's some. Okay, let me say it now. So when you do quantum computing, you discover that in some sense it's all about how you encode the state. The naive encoding of a quantum, so a quantum state of n qubits, the straightforward encoding is 2 to the n factor. It's exponential. But some states have easier, like smaller encodings. So not every state has to be 2 to the n. So you can sometimes find smaller representations, and people dynamically change presentation. This is the interesting part. So they start with the representation presented this way, and then they kind of do some compilation, it becomes big, so they switch another presentation, and so on. So it's all about kind of like finding the right alphabet, the right symbols to encode the states. How nature does it, we have no idea, I have no idea. But if we're simulating a quantum computation, we might want to switch representation to try to stay within the, and one of the, I don't mention the theorem here, but quantum states with superposition and entanglement in a certain class of them can be classically simulated efficiently despite having high entanglement and superposition. This is the Gauss-Mendel theorem, that there's a big class of quantum states that the naive simulation will be 2 to the n, but they actually have an efficient presentation. So you look puzzled about, this is a very original example I invented, the power example. You may have seen it before. Okay. Representation dependence, I don't think I need to tell you what it is about. I was trying to kind of give them lots of pictures. But it will come back, it's important, it will come back like in the, but again, the point is, I mean, the advantage to quantum is the following, is the quantum state where you know how to interact with it, but you have no idea how it's represented. And you can never know, and this is a secret of nature in some sense. And we'll get to that when we try to model quantum computing. Okay, you know sorting, that's boring. The reason I mentioned this is because I prepared an initial deck of slides, showed it to Gerardo. I've been working with him for a long time, and he stopped me at this slide. This was the second slide, or the first slide. And he stopped me at this slide and argued with me for half an hour. It's like, what do you mean, what's the word? Yeah. Is that a single demonstration of quantum advantage? It's like, no, there are lots of demonstrations. And he kept giving me George, quantum this, simulation this, that. It's like, anyway. So try to understand lower bounds, upper bounds, big O, worst case is difficult. So that's why through sorting, it's like, if I sort using an n-squared algorithm and somebody in quantum says, hey, I discovered an elegant quantum algorithm for sorting, it's like, I don't care, because there's a classical one. So is there a classical factoring algorithm? We don't know. Unlikely, or I don't know, whatever, but maybe. So it is possible. So the point is, there is no kind of formal result that says there's a quantum advantage. And there's no practical result either. There is potentially, like these educated guesses, or like, you have like something must be going on, and you think that there's an advantage, and there's lots of evidence that maybe there's an advantage, but nothing is conclusive yet. So this is an important thing. And at this point, somebody in the audience asked about, well, what about such and such, both Google and IBM claimed quantum advantage. So we'll get to that at the end. So this will be the punchline. So don't trust Google or IBM or Nature. Because they both publish on the cover of Nature. Okay. So obviously, YCS perspective, well, because we have a new set of classes. I'd like to start with, does anybody know Henry Baker? I'm old. You know Henry?
The more things change, the more.
Yes, yes. Oh, see, he's he doesn't have white hair, but he does. So he was very. I mean, he's an interesting person. He had like very kind of new revolutionary kind of ideas, garbage collection and computer, this thermodynamics of quantum, thermodynamics of garbage collection, stuff like that. In 1992, he said there's a physics revolution brewing in CS. And I think he was right. He kind of put the finger on, and he talked about many things. But did it happen? Well, I don't know. Maybe it's happening now. But this is an important thing. Like CS, from very early, it's like there's something going on here we need to understand. Okay, so here is the first theorem that I think is crucial, and we need to kind of understand this theorem. So, quantum mechanics is whatever. We don't care about quantum mechanics. we care about quantum computing, which is controlling quantum things to do computation, right? So you abstract, and the abstraction that people have is qubits and circuits, gates, qubits and gates. There's many other abstractions, but this is the dominant kind of popular one. And it's a fine way to think, so we have wires that carry qubits, and you have gates acting on those qubits, and you have a circuit. Just like you study in whatever 335 or whatever, you can say there's a bunch of N gates, do addition, and whatever. Okay, so we have this model. Now the question is, what set of gates is sufficient? Remember, these are real numbers, which you can encode as complex numbers, which you encode as real numbers. But real numbers, well, there's an issue now about, these are infinite, things. So how much precision do you need? How many real gates do you need, and so on. So there is something I never understood, a theory by Kitaev, maybe you know it, or understand it. I never understood it. I mean, I understand the statement, but the theory was like deep stuff that about which sets are dense in which sets, and how to approximate which real numbers with what real numbers to within absolute error, and so on and so forth. The result at the end of the day is two gates. One of them is classical, are sufficient to encode quantum computing if you are willing to pay polynomial overhead, which is fine, which is lambda calculus kind of overhead. Okay, so you can encode everything using these two gates. So I'll tell you what the gates are in a second, but that's what it is. And this notion of computation universality is not well known. We submit papers and it's like, what are you talking about? Define it. And in some sense it's fair because one result is coming from mathematics, not precise result, and the other result is an archive paper that is not even officially published. But it's it's well documented, well established, and people have redid the proof, and now it's folklore in some sense. Okay, so we have these two gates, and they are sufficient. So if you're thinking of like the minimal lambda calculus-like language, this is a good candidate. You have one gate which is Toffoli, and one gate which is Hadamard. So what are these two gates? So Toffoli is controlled negation. What does that mean? You have three inputs, x, y, and z if you want. If x and y, then not z. That's all. And otherwise you return the same thing. Okay? Because everything is unitary and reversible and so on, you actually return x and y, you keep them so that you can go back. So x, y, z goes back to x, y, and then the third wire is x and y, x or z. Okay? So you flip z if x and y are true. So this is a classical gate, and it's universal. People, this is obviously called Toffoli. Mr. Toffoli did not call it Toffoli gate. He called it the generalized NAND gate because it is like a NAND gate in classical computing. It is universal. The universal gate for reversible classical computing. So Hadamard we'll talk about a bit more, but is there, okay, so we know that this is, if you're here, they're completely classical. There's absolutely nothing quantum. If you're all together, you're universal quantum. So the question is it like a sharp transition? Do you have to get everything? Is there like what exactly is happening? Is the question.
You said if you're all together,
if you're Toffoli and Hadamard,
okay.
If you have an unrestricted use of Toffoli and Hadamard, then you're completely universal.
Yeah, that's previous stuff.
Yeah, but exactly, yeah. So I'm saying, but is there like a transition somewhere, that, Now, the Hadamard gate, again, this is a gate that predates, quantum. Monsieur Hadamard is, from friends of Fourier and so on. So these are ancient people, prehistory. But it's all about kind of like, it has the flavor of Fourier transform, and it is actually the special case of Fourier transform on the volumes. So it is the Fourier transform. So it is now telling you that another way, if you want to think about it differently, you can say, well, classical computing plus Fourier analysis, Fourier transform, Fourier, something is quantum. So it gives you a hint that there's something about waves and frequencies that is embedded, that kind of like deeply embedded into quantum. Okay. Okay, questions? We're kind of okay. So what we have now is we have from that theorem we have a characterization of quantum as reversible computing. CCX is just one way to model reversible computing. I mean, I don't like to compute with bits, so I'll try to find something other than CCX to represent classical computing, but it's a proxy for classical computing. So take any classical kind of base language you prefer and add to it Hadamard. Or something that does the function of Hadamard, like whatever Hadamard is doing. So you can think, okay, I'm going to add Fourier something on top of my classical language. But there's also different ways of viewing Hadamard, and maybe one of those ways is more interesting as a way, if you take an arbitrary classical language and try to add something to it, maybe adding a square root of a function, because the Hadamard gate is known to be the square root of Boolean negation in the quantum. So maybe, so what does square root of function mean? Well, figure it out. There's another way, which is exchange of bases. Let me talk about these two things. So quantum computing over many, many qubits does not have a very good geometric kind of picture, but over one qubit is very beautiful. It's a sphere. The north pole is 0 by convention. The south pole is 1 by convention. So you have classical computing are the two poles, and you can obviously go from one to the other. And that's it's called the X gate because the orientation of the axes is Z, X, and Y. And so rotation around X gate, or rotation around the X axis brings you from the north pole to the south pole. And that is, for us, is negation. Like you go from 0 to 1, from 1 to 0. So, but if I stop in the middle, what happens? I mean, in classical computing, of course, in classical computing, transistor that is going to flip from 0 to 1 will go continuously, the voltage will change or whatever, but you cannot observe the bit state. You have a clock, and you can only see things, in discrete steps. But in quantum, and this is crucial, you can see the intermediate steps. And when I talk to the experimentalists, they tell you, it's very easy for us. We have a laser, and you shine the laser, it gives energy to the ion, and then the ion can go from 0 to 1. And if you give half the power to the laser, or shine the laser for half the time, it goes in the middle and it stops in the middle. That's what it is. So it's very simple. For the experimentalist, it's very simple. Square root of square root. It means I shine the laser for half the time. Okay, so there is kind of this idea that you can navigate the entire sphere and not just the two poles. So you're at the 0 and 1, but you can go halfway. And of course, once you go halfway, you can go make a little turn around the equator. You can go a little bit this way, and you still start exploring. And that's what the theorem says, is you can explore the entire sphere by enough approximations. Yes?
Oh, why is this the sphere and not the circle?
It's the surface of the sphere.
Sure, but a sphere has another dimension.
Yeah, I mean, it is a 3D, yeah, it's also very...
Right, but I'm trying to if we just think about going halfway from 0 to 1, or any other distance, then we only get a circle.
Yeah. But I mean, I said it kind of in a hand-wave way, but okay, you go halfway around, you go to the equator, and then you can go around the equator. And that's the phase, that we'll talk about that. But so you have two things. You have a direction, if you want, of where you're pointing, and then you can go down. And then there is an Euler decomposition that essentially tells you if you have two axes and you can rotate around each, then you can get anywhere on a sphere. So there's like some kind of geometric things, but okay, so this kind of brings us to this point here, which is you pick two axes, z and x, arbitrary, I mean it's a sphere, pick any two axes, orthogonal obviously. If you live along the z-axis, this is, you see 0 and 1. You don't see anything else. So you're completely classical. The other axes,
Here's Professor. Break your board focus.
to do this again. Okay. So if you live along the z basis, you see 0 and 1. The x basis is another random kind of axis, and it also has 2 points when it meets the sphere. And you can call them false prime and true prime if you want. So you have another kind of 2 extreme points. And Hadamard is characterized as it changes the basis. So it takes you from this basis to this basis. So for now, let's leave it at that. But anyway, so the point of all of this is there are lots of possible ways of thinking of what Hadamard is doing. So we are going to try to, the whole game now of this talk is going to try to think of how to represent Hadamard. CCX is going to be a classical language that's boring. We invent a classical language. But now we want to invent a way to kind of embed Hadamard in that language to get quantum and get some insights out of this. We don't want just to kind of add Hadamard. I mean, that would be correct, but kind of uninspiring. Okay, that's what I said. Okay, so we're going to start now a little bit of, how much time? Oh, I left my phone downstairs on purpose.
Do you want to know the time?
4:20, I see it here, 4:25. Okay, so let me rush a little bit. Okay, so this is an example circuit template, because it doesn't have all the gates, but it's a template for essentially all of the algorithms we know. I'm exaggerating a bit, but all of the algorithms we know, including Shor, which is the most important one, have this structure. So what is the structure of these algorithms? Well, you have a bunch of qubits here, a bunch of qubits here. These are the ones you care about. This is the interesting part. These are kind of auxiliary storage that you need to kind of do the computation. Usually it's initialized to zeros, so this is kind of general case, but usually it's just a bunch of zeros. The first thing you do is you do Hadamard. And I'll explain what does that in a second. After that, this is, you can think of it as a bunch of CCX, which means this is a classical thing. So do Hadamard, a bunch of classical things, QFT, which is Hadamard generalized, and then measure. So Shor's algorithm is very weird. That circuit here is a circuit for multiplication or exponentiation, like a circuit that you could give as an assignment to an introductory computer science class. Define a circuit for multiplication using adders and whatever. So that's very boring. Hadamard is just this one gate at the beginning, at the end, and that's it. And this is supposed to be an exponentially faster, as far as we know, circuit for factoring. And this is kind of like, when you think about it, it's like, where is the magic? Okay. So let me give you a little bit more details. Okay, so this is the one slide I want you to follow. It's a little bit tedious, but not too tedious. Okay, so this is actually hand-optimized circuit to factor 15 using Shor's algorithm. So the hand optimization comes in, I kind of looked at the optimal gates that I need for that block, UF block. Okay, and I kind of minimize number of qubits and whatever. Anyway, so there's 3 qubits who I care about at the top, and 3 auxiliary qubits down there. Okay, so what Hadamard is going to do is going to take you from the computational basis, which is the classical basis, to this other basis. So here's the thing. When I am at the North Pole, I know I'm 0. If I go to the equator, I know I am 0 or 1. I mean, between 0 and 1. So this is represented as 0 plus 1, vector. So we get back 3 Hadamards. Each qubit is 0 plus 1. So you get all 8 possibilities. So the top 3 are 0, 0, 0, 0, 0, 1, 0, 1, 0, blah, 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 all the way to 1, 1, 1. So the first thing you do is Hadamard is moving you to the equator for those 3 qubits, and now they are in a state that is kind of in between 0 and 1. Okay? The bottom 3 qubits are 0. We're not touching them. Okay? So now we have all of these possibilities. This classical representation is exponential in number of qubits, the 3 qubits, but that's fine for now. And then you have these 2 gates. And these are Toffoli gates, but only acting on one control, I mean, like a special case. So the second one here says if the x0 wire is true, negate this guy, and this one says the opposite. If it's false, negate. Boring stuff. Okay, so just the first step, for example, for this one here, if the third qubit is 0, negate the last one. So it used to be 0, 0, now 0, 1. And then whatever. This is 1, so does it change? This is 0, it negates, and so on. The next step does the same thing on another qubit. And then you just kind of rearranged. So this is like a giant vector. And I kind of grouped them in a different way to make it more readable. So you notice that after you did the Hadamard and the 2 gates, you get to that state, and if you rearrange it, it looks this way. So somehow, this is very interesting, the bottom 3 are now all 001 or 100. This is magic, right? I mean, this is somebody very clever worked to make the algorithm. I mean, in this case, I reverse engineered it, so it's not surprised. It's not surprising, but to come up with the first algorithm is very interesting. Anyway, so now at this point, you have a bunch of states that have 001 in the bottom 3 or 100 bottom 3. So to simplify, it's not absolutely essential, but simplifies things quite a bit. Measure the bottom 3. And quantum measurement is one of the mysteries, but mechanically it's very simple. Mechanically it says, well, there are 2 possibilities with equal probability. So if I measure the bottom 3, I'll get one of them. So I'll either get 001 or I get 100. But if I get 001, all of those are impossible anymore because they're not compatible. So if I get 001 on the bottom 3, the top 3 are going to be 0, 2, 4, 6. And if I measure 100, the top 3 are going to be 1, 3, 5, 7. Nice sequence. So 0, 2, 4, 6, 1, 3, 5, 7 have the same frequency if you think about the repetition pattern. And the quantum Fourier transform doesn't care about the initial kind of displacement, initial phase. It cares about the pattern of repetition. So you feed either, so it doesn't matter which one you feed to the Fourier transform, it will tell you the period of that sequence is 2. And that's the game after that is classical number theory to go from that to the factors. Okay? So this is how this kind of algorithm works. So where is the quantum advantage? You tell me. Well, I mean, obviously the classical simulation of that circuit has this exponential, size thing, and maintain that exponential thing and act on it one at a time. Obviously, that's not efficient. But if there is a way to kind of run this without blowing up the exponential kind of representation, then we do it. Okay, so on sabbatical I had a dream, and then I was like, something that is, yes.
So, are we factoring anything yet? Because I just don't know how to factor.
In a way, yeah, okay, I kind of knocked on and I said, given the period, so, okay, given this period, there is some number theory kind of post-processing that gets the period. So the big picture is the following. To factor n, compute the period of a to the x mod n, where a is coprime with n. From that period, you do some small calculation to get the factors. This is like a classical number theory result. So the Schur algorithm actually doesn't do factoring directly, it computes the period of a to the x mod n. Okay, so when I was thinking, it's like, okay, so why do I need this giant representation? And something that is either 0 or 1 sounds to me like an unknown variable. It's a variable, logical variable, some kind. X, I call it X. And then C, I have to compute partial evaluation with these X's. So I remember this was, I was at my mother-in-law's, and I was kind of hiding and doing this stuff. And then I wrote some code. I'll come back to it in a second. So I wrote some code and ran circuit, and circuit has, yeah, the factoring 15 has, so you add all of these, like 50,000 gates. And I produced a circuit using boring multiplication and addition. So I was starting from AND gates and OR gates, and build a half adder and an adder. And so anyway, so not very simple, not very smart circuit, 50,000 gates, and I ran it, and it gave me this. So what does that mean? I mean, it tells me that there's three variables, x0, x1, x2. x1, x2 are unrestricted, and x0 must be 0. Means it's an even number, which means the period is 2. And I jumped and I screamed and I got out and what's going on? I was like, I tried to explain to her. She was like, I'm happy for you. That's what she did. Anyway, so basically, n multiplied to 0 is a variable. That's either 0 or 1. So I'm going to make it a Boolean variable. CCX is the general case. In the example we have here is CX, just one control. It's A, AX, or B. So just compute with variables and symbolic things and see what happens. So here is, for this particular example, here's the way it is. So what we're going to do is, we're going to say, like the top variables here, we're going to call them x0, x1, x2. We are going to pick an arbitrary result that can happen here. You can compute this in different ways. You can run the code once with like one fixed input and see a possible output. Or you always know a to the x mod n, well, one of the outputs when x is 0 is 1. So you know that 1 is a possible output. And the Fourier transform doesn't care about which, one you get. So you can always pick 1 in the case of Schur. So you can always pick 1 for the bottom 3, some no variables for the top 3, and then you compute symbolically. So it's like, okay, what is x0 control not 0? Well, it's x or is 2, which is x0, and you compute whatever, and then you have initial conditions that tell you these are all zeros, so you get initial conditions, and seems very nice, very beautiful. It's like, okay, you're giving my Nobel Prize. But it's not quite that simple, because in this case we're lucky. Sometimes those equations get huge. So, but what I discovered in playing is if you choose another basis, another variable representation, you can always kind of bring it to a smaller kind of set, but there is no systematic way of doing it. If I know the result, I can always find a small representation, but there is no systematic way to do it, as far as I know. So anyway, it's kind of interesting, but it doesn't necessarily tell us how to solve it, but it gives us a hint that it's kind of all about how these relationships among the variables are represented. Okay. And like a side effect, side kind of story here is that I had to execute backwards and maybe run forward once and whatever. So we had this kind of idea that because these are reversible circuits, we can actually run one, not exponential, pick one input, one sampled, run with one sampled, get the possible output, go back with that possible output like I did, and then go and see what happens with the Fourier transform. And this was with the work with Gerardo, and Gerardo was like, oh, but with quantum mechanics, and we talk about retrodiction, and count how the past can determine the future, and you see a tunneling effect, can you determine what happened before the tunneling? And so people have, so it connected to a lot of kind of interesting kind of history about quantum mechanics. Anyway, and then I discovered that there's nothing new under the sun, because many millions of people have been working on Boolean functions and Fourier kind of methods to learn Boolean functions. And so this is when it's like, okay, maybe I should learn a little bit of try to understand. I've been avoiding it, but now maybe it's. So another way to think about everything that we've done here is a hidden Boolean function. And then you're trying to learn something like its spectrum. Like how many times it flips, what's the period. And this is an old topic in math and CS. And I think that this is an important tie, I think, between learning Boolean functions and quantum. So I think there's a very intimate tie here. It's not my thing, but one day, if I ever get there, I'll try to look into that.
So thinking about this, is if you take the symbolic execution approach that you did, that is factoring. It's a classical algorithm for factoring because you're running it on your computer. Do you know what classical algorithm for factoring? Is there a Fourier transform algorithm for factoring that it is implementing?
Yeah. So this is closer to solving SAT problems. In some sense. It's like, and people have used SAT solvers to factor, and some SAT solvers are based on Fourier methods. So yeah, so there is. This is how I connected all of this, and it's like, okay, this is a deep kind of.
So you could think of this as like doing SAT to implement, doing Fourier analysis to implement SAT to implement factoring on some bit width.
Yeah, yeah, and it seems to work actually well. Obviously for some cases, but SAT is pretty good, and a lot of them are based on these Fourier methods to try to get the spectrum of how the things are distributed and so on. So I think it's a fascinating area. It's like why is it hard? It's not even clear why that is hard. We're trying to, because this is all conjectures. All of these kind of assumptions in complexity, cryptographic hash functions, and they're trying to make it hard for you to discover the pattern, so that a few samples will not give you enough information about the pattern. So they have to work really hard to hide the pattern, but it's not clear that it is a hard problem. It's, again, one of these open questions. Anyway, so now we get into the fun part. Okay, let's go quickly. This is easy. Abstract type board. You've all seen that. But what I'm going to do is something I mentioned briefly earlier, which is I can do obviously anything inside. So in particular, I can choose vectors along any of the two axes on a block sphere. And it's completely hidden. Nobody knows anything about what's inside. So I can choose to represent true as the vector 1, false vector 0, not as the x gate. Copy. You can copy classical things. So you can duplicate them, and you can do the inverse of copy, partial inverse. So this is all classical stuff, but it just happens I'm representing false and true using vectors. I can also present them using some other vectors. So this vector is 0 plus 1, and this vector is 0 minus 1. They are the 2 points on the x basis on the equator. So I pick 2 points on the equator, opposite points, and I say, well, true is that point on the equator, and false is the other point on the equator. And again, from the outside, nobody knows. And they're both classical, there's nothing new, there's nothing interesting happening. Two classical languages with hidden representation. One is using 2 points on the North and South Pole, 2 points on the equator. Okay, now here's something very strange. Of course, you have equations to constrain that you don't make nonsense. So there's like an interface to the data type saying you must obey certain equations. So here are the equations. There's one more equation. There's some equation here. These are the boring equations. The boring equations tell you that copy and inverse copy are inverses. Copy is, you cannot distinguish the two things. You can swap them. It's the same thing. There's some kind of, you can copy A or copy the other guy and you get the same thing and so on. So these are all kind of any classical implementation of copy that you can think of will satisfy these, and it's very simple. Then we have another equation, which is very strange. Because, so if you notice here, all of the nodes have the same color. So they are pick one implementation of like one of these data types and reason about it. So one, whether it's the first copy or the second copy, they have to obey this. In this one, we're mixing the two data types. So I have one data type that you provided and one type that you provided, and they are each saying I'm a Boolean variable, and now I'm going to make you talk to each other. What does it mean? Because you don't know what is representation and vice versa. So what it means is, I don't know what it means, I don't care what it means, I'm going to impose this equation. That if I ask you to copy and then take one of your bits and one of your bits, ask you to copy, feed them to you, ask you to inverse copy, and then ask you to copy, it should all be the identity. If that is true, this is quantum computing. And that is like enormous. There is an explanation, and that's all there is. Because, sorry, but I know it's crazy. But okay, I think tell you what this equation is called. This equation is called complementarity equation. And if you read anything about history of quantum mechanics, or in 1920 or 30 or 15 or whatever, not 15, he said complementarity is the defining characteristic of quantum mechanics. It's the momentum position kind of. So here's the idea, is that you have to have a situation where, so let's think back about the X basis and the Z basis thing. So if I tell you I have two variables and they're both true. Okay, you know they're both true, so you know the values. But do you know they are both true because they are correlated or just by coincidence? You don't know that. So you have zero knowledge about their correlation, but you have all the knowledge about their values. Now, vice versa, if I tell you I have two things that are equal, they're correlated, they are always the same. So you know they're both true or both false, but you have zero knowledge about their value. And the equation is enforcing that, is that if I know your value and I feed it to the other one, I lose all information about the value, and vice versa. So you cannot retain information between the two bases. So they have to be complementary bases. So the two choices of Booleans have to be such that this Boolean means nothing here, and that Boolean means nothing here. Maximally kind of nothing. And if that is the case, this equation forces that, and if that is the case, then this is quantum. So again, another way to characterize quantum now is two classical languages. So I have a picture, I think. Okay, that's the theory. So you can actually write the circuit that we had before, something like it. Classical language 1, classical language 2, classical language 1. And then you put, these kind of, you force them to interact, and it's quantum. If they are the right, complementarity-oriented languages. So it is two classical language, two different perspectives, two different classical perspectives that gives you quantum. Of course, there's no advantage in computing each one of them separately. I mean, there's never been a quantum advantage of speed up if you live in here or here separately. The interaction is where the speed up has to be. if the change of perspective is efficient, then this is all efficient. So it's all about that the change of perspective from your Booleans to your Booleans is very hard to compute. That's changing the perspective from one set of Booleans to the other is not easy to compute. If it were easy, then this would be all easy. Okay, so I have a whole bunch of slides on the categorical stuff which are kind of irrelevant. Trust me, the details. But here's another, the other perspective, very briefly. We mentioned briefly that in a digital processor today, you have a clock. I mean, you don't see the thing in between. But if you were to see the things in between, you would see this kind of in-between states. So if you could slice time differently, so you run on a clock that is 1 second, you on half a second, you on a quarter of a second, you on 2 seconds, and you can observe the intermediate states between different computations. Then again, this is quantum, because Hadamard is the square root of naught, which is exactly the halfway step between, like if you take a NOT gate, cut it in half, and say, okay, this is now a unit of computation, this one's another unit, and I can compose these units, then again, this is quantum. So again, this is a much kind of more involved proof, and there's a bigger story to kind of prove this, but I mean, the proof is done in a very axiomatic way. This is the categorical perspective where you just have a category for cloud computing. You postulate, two gates that have that's when you postulate a gate that when you compose you get the X gate, and then you postulate something else, another equation, and then you prove that this is a model of quantum computing. And then you can reason about it and you can get the equations. I mean, there's a lot of details, but that's kind of the idea. I kind of mentioned that. So there's that kind of weird equation that you have to impose that is the magic sauce, which we don't actually know why. I mean, this equation was discovered by the usual way. You try to do the proof, if something doesn't work, so you add an equation, it works. It's like, okay, so this equation is what you need. What does it mean? It's not totally clear. You have some ideas, but it's not totally clear. Okay, so it's quantum. So now let's kind of argue. Okay, so this is the IBM claim, cover of nature, evidence of big words, and then so this was June 2023, January 2024, 6 months efficient simulation of the experiment on a classical computer. So, and then somebody actually after that did something else that made it even more. Discovered that all of these qubits is essentially like one computation, lots of noise and repetition and whatever. So anyway, so that's not practical. I mean, so there's no theoretical advantage because we don't know what factoring complexity is. And these kind of big claims, well, they don't quite work. The other one about Google, that was earlier, that was in 2019. And again, it can be done classically. Okay. So take whatever you want to take out of this. You can say that people are overselling, which is definitely true, but also that it is actually hard stomach. It's not, it's hard to kind of, it's very subtle and it's hard. Yes.
So what you said earlier is that all of these algorithms are like about hidden subgroups. Are any of those hidden subgroups like known to have some particular complexity? So they're all in the same state as factoring?
So the reason actually, so there's another thing I didn't mention, but so Shor algorithm is unique in that class because it's, you know exactly, you have the full circuit. Other algorithms, except for Grover, talk about it separately, are black box model of computation. So you're comparing how many queries to the black box.
Okay.
Classically versus quantum mechanically. but you don't have access to the black box. And so in that case, there is a proven advantage, but to build a black box in practice, it's exponential. Right? So it's like but if nature had a black box to do one of these things, then the classical computer would be at disadvantage. But if you are trying to use Grover's algorithm to speed up some search, well, you have to build the black box. So, yes, that one is more subtle. I've seen papers where people try to, so Grover algorithm is just a generic kind of search, which is kind of also very strange in some sense, that an arbitrary search of unstructured data can be done in square root of the number of things, which is like, how? Okay, whatever. But it is possible if you have this black box model. So people say, okay, let's, for example, and I've seen this paper, it's like, okay, let's try to speed up, like we have a compiler, the compiler has to do some kind of search for, whatever, maximally, components, whatever, to do some kind of data analysis, whatever. So let me use Grover to search. Well, to take the data to feed it into that black box, basically kill the algorithm. So you don't get any advantage.
So is it possible that quantum computing provides advantage over classical computing only in these hidden subgroup algorithms?
So when you go back to this kind of, go back to the very first theory. Were you here for it? I don't know if you were here. The Toffoli Hadamard. So the only difference between classical and quantum is Hadamard, which gives you some frequency analysis capability. So the only possible advantage would come from some learning some properties of functions that are kind of, the periods, number of repetitions, that kind of stuff, which all have this kind of hidden subgroup kind of flavor. Learning Boolean functions, spectrums, I don't know. So it doesn't seem that there'll be another, but it doesn't mean, this is one perspective. There's other ways of characterizing quantum computing based on this adiabatic thing, this measurement based, I don't know what. There's different ways, and maybe those would give you some different perspectives. But again, they're all Purlinian equivalents. So,
but in order to get some quantum advantage on some other algorithm that we don't know yet, we would need to be able to get some advantage by doing Fourier analysis in some portion really fast.
It seems this way, and when you put it in those words, it seems very pessimistic that it will happen. But again, I don't know. Computer science is full of projections.
Weird things happen.
Yeah, unknowns, and we don't know a lot. There's a lot we don't know. So, anyway. If you want, so she's a very, I like her. She's a respected physicist. Sabine, forgot her last name.
Hausfelder.
Yes, I knew it was like our Hofstadter, but not another. But anyway, she's this particular video is very good. But she's a skeptic. She doesn't believe quantum will ever happen. But I don't know. And then if your picture is not here, maybe it could be next time. So, who's that? Anybody knows?
I think it's Charles.
Yes. We tried to find his picture, but he doesn't have any pictures of himself. It's like a mystery man. That's it. Thank you.
Sam here. Is Sam just So you have to go. Well,
Yes.
I'll ask Amr what Sam meant. So, isn't it that you want Fourier transform to be slow in order for quantum to? Isn't it that you want Fourier transform to be slow so that you can get a quantum advantage? I just got the signs confused. Like, why is it test method?
No, you want to be able to do fast. You want to, okay, let me talk to you in your probability language.
Sorry.
You want to be able to sample efficiently from the Fourier distribution of a function. So take the function e to the x mod n, and then take Fourier transform, and you want to be able to efficiently sample from that. And it's unknown how to sample efficiently from that. It's one.
And in the case of factoring, it is known, or
No, I mean it's known quantum mechanically, but not
okay,
classically.
sure, but
Yeah,
that,
yeah.
so isn't that good news for quantum that we have hoped to have an advantage?
Oh yeah. I mean.
So
but
it's
everybody's-
pessimistic
yes,
in one
yes.
sense, but
Everybody's betting on shore. Yes.
okay, but the
Yes. You're right. Yes.
okay.
So why is classical factoring difficult? I mean that's good.
Okay,
Maybe
it's
because-
pessimistic for people trying to classically break
Yes, yeah.
factoring. Okay. I'm so confused.
Good. That's the point. It is. It's not a black and white thing. It is a very subtle kind of thing, and nobody knows where the advantage is. If there's an advantage. A very
Is
strong.
it, do you have a thesis, or is it like a modernist novel?
Do I have a thesis
Yeah,
about what
like
the
what's
result is?
what's your what's your point, like, or
I mean, what did I say? Here, no clue. I mean, I wish I knew if there's an advantage or not. When you think about it, I mean, so the mystery is how does nature do it, right? I mean, it seems that, I mean, everything around you, I mean, this thing uses quantum mechanical, the GPS, the laser, MRI, these are all quantum things. So they are using quantum properties. But they are using quantum properties as they come without your control. I gave this analogy to my son, actually. Controlling wind is different than using wind to fly an airplane. Wind is there, and then if the wind goes this way, you go this way with it. You have some control, but not huge control. But to actually control every molecule of wind and make it go the way you want, and stop tornadoes and make tornadoes, that's a different level of control. That's what quantum computing is about. You are controlling billions of qubits to make them dance the way you want.
so what's the mystery? You say there's a mystery. I don't see a mystery. Like if you're used to how we cannot control wind, then there's no mystery how we cannot control.
Yeah, but
Quantum.
who says that we cannot tomorrow? We won't be able to do it.
So what's the mystery?
There's no mystery. We don't know how to do it. That's all. I mean, no clue. That's the mystery. I don't know if it can be done. Nobody knows if it can be done. You can control 10 qubits, 100 qubits. Can you control 1 billion qubits? I don't know.
Okay, look, I have a different question. Like, what's the relevance of representation independence? Like you talked about, different representations of complex numbers and so on at the beginning, but
Yeah, so-
how is that figuring
So
related?
when I did that symbolic execution, I
Yeah,
kind
why
of-
is that related? How is about, how is it related?
So a quantum circuit with fully entangled quantum qubits, many qubits, 10 qubits, I was able to simulate classically in like this. Because of the symbolic execution, all canceled quickly. I didn't have to go to the 2 to the n representation. So I didn't represent the 15, I think, forgotten. Forgot what they were.
Okay, right, so you have some ideas about how to do classical simulation efficiently or more.
So here it tells you n is equal to 12. That's 12 qubits. So 2 to the 12 vectors running over whatever, 200,000 gates. That would take a time. But this was instant, right? So the naive representation for this computation would be 2 to the 12 vectors, size vectors, running through 200,000 gates. It just happens that the symbolic representation, I just don't present vectors out. I call them X, Y, and Z, and I code symbolic execution. And just happen X OR is very beautiful when it aligns correctly because it cancels. You know, A, X OR A disappears. So you find like this thing kind of like disappears and shrinks and becomes very efficient. If you have certain other inputs, they don't cancel. It gets bigger and bigger and bigger and bigger. You switch to another basis, base 3, base 5, base 7, they shrink again. So if you find the right basis, you will never kind of get exponential blow up in the size of first stage.
So are you drawing some kind of, are you is this saying, are you saying it's like the way things cancel out in symbolic execution is gives you hope that you can somehow generalize the subgroup problems?
No, I'm saying not all factoring problems are equally difficult. There are many that are known to be easily solvable classically. And it just happens that the ones you can solve classically efficiently are the ones that lead themselves to lots and lots of cancellation. And this method also solves them classically. I didn't discover a new class that can be done efficiently. It just happens that the ones that happen to do efficiently are the ones that other methods can do efficiently, because the problem itself happens to be easier in that instance.
I guess I'm not quite sure which part. I mean, I feel like there's two talks you're giving. One is about how to simulate efficiently, and one is something about not having a clue about quantum advantage.
But I can only simulate certain things. So I can only, so okay, I mean, what is quantum advantage? It's the separation between classical and quantum. I mean, that's the advantage. So on one hand, I'm trying to understand where the boundary is. What other things I can do classically that what are things I can do quantum mechanically I cannot do classically? So is there like a line that this problem is here, this problem is here? We don't have this line. I mean, we have, just like P versus P, we have like fuzzy dotted lines, but we don't have a sharp line. So I don't know. And on the other hand, I'm trying to see, like, push the classical envelope and see how far can I push it, simulating things that look quantum, but can be done classically. So there are many things that look quantum that can be done classically. And characterizing those is also useful, because it tells you that those things that look quantum in that way are not quantum.
Okay.
Okay, thank you.